At long last, it is the day you've been waiting for. We get to look at the structures of the 20 common amino acids. We're going to draw each and every one of them. And the best thing about amino acids is quite simply that they are like people. Every single one of them has its own personality, and each and every one of them has some environment, a regional location within a protein in which they are they most thrive, in which they are most accommodated. So we will keep that in mind as we look at every one of their structures. But before we dive in and start drawing these structures, I want you to recognize that the projections that we're using are Fisher projections. So rather than having to draw all of the stereochemistry, in a Fisher projection, that is implied. So the bonds that are horizontal, we can always assume are coming out of the page at you, and the bonds that are vertical, please assume that those go into the page vertically. The vertical bonds go back into the page away from you. So that gives the stereochemistry that we would expect around, in this case, that central alpha carbon. As we begin to draw the structures, let's begin with the simplest of the structures. This one is glycine. Glycine, remember, is one that we already began to meet, and we recall that it is the only achiral amino acid because it has only 3 substituent groups around the alpha carbon, so the hydrogen is repeating. The simple hydrogen, however, gives glycine an incredible personality of being ultra flexible. It can get into tight spaces. So glycine's 3-letter abbreviation is GLY. Its 1-letter abbreviation is G. Now, I recommend that you draw all of these out, you promptly take your notes and post them somewhere where you look all the time. Maybe it's above your sink where you do dishes all of the time. Maybe it's, in your bedroom where you lie around all the time. I don't know, maybe it's in front of your toilet. Wherever it is that allows you to frequently see these and frequently study these and learn them, that is where you want them to be. Notice too that the alpha carbon in this is achiral. It's not chiral. It's the only amino acid like that. And notice that this fits into small spaces. It is flexy. It can be in tight turns, in tight places. We know people like that who thrive in those tight spaces. So it, in that way, can accommodate, there is no other amino acid that can be accommodated in those really small and tight spaces. Alanine is little too. Alanine is got a simple methyl group as its R group. ALA's 3-letter abbreviation, ALA, quite straightforward, and its 1-letter abbreviation equally as straightforward is simply an A. So as we start to recognize that we're looking at aliphatic R groups, aliphatic R groups are those that have hydrocarbons that are either linear or branched, or in one case that we'll look at, the branch kind of wraps back around and forms a little bit of a ring. So we begin to see that with alanine we're looking at the simplest hydrocarbon. Valine becomes a little bit more complicated. But valine is super easy to remember because its R group actually forms a V. Check that. Now, when we begin to start seeing hydrocarbons accumulated, these non-polar carbon-hydrogen bonds, we can think to ourselves that this amino acid probably really hates water. So its personality is very highly hydrophobic. So Val, V, it's going to want to live in a landlocked state, right? It doesn't like much to be around water. So it is very highly hydrophobic. Water hater. And the next of our amino acids are also very highly hydrophobic. Leucine even more so than valine because you add yet another hydrocarbon in its R group. So rather than having just the simple 3, it has 4 hydrocarbons, a very similar structure to valine, only there is an additional carbon bound to 2 hydrogens here in the beta position, so the beta carbon. Now leucine has a 1-letter abbreviation of L and a 3-letter abbreviation of LEU. Makes a lot of sense. It's another highly hydrophobic amino acid, so we can jot that down. Highly hydrophobic. I have a shorthand that I use for that. I just go like this. With like a 0 with a slash through it. It just means highly water hating. No water. No water. So we're gonna leave it at that because it's helpful to have a little bit of extra room here. Now isoleucine, this is a really special amino acid because it's a lot like leucine, only the branch takes place up above. So we actually will recognize it as having an extra carbon branched off of its beta carbon rather than gamma. So this is what we're looking at for isoleucine. Now, isoleucine is clearly also highly hydrophobic, but it's a super fascinating amino acid, the first one that we've met that actually has two, not just one, but two chiral carbon centers. So notice this, I'm going to put a star by both of the chiral carbon centers. Of course, the alpha carbon, but so too the beta carbon. Both of them are chiral. So that being said, let's take just a minute to look at the 4, not just 2, but 4 stereoisomers of isoleucine. And you're getting the chance to meet my cat, Gabby. Gabby is making sure to make my job difficult of writing stereoisomers, but we're going to do it anyway. We're going to forge ahead, difficulty accepted, and take a look at all 4 of these different stereoisomers. Let's begin by just simply drawing isoleucine, recalling that, of course, it has its typical alpha carbon, carboxyl and hydrogen, but then as we get into the R group, recalling that we had the methyl group attached to the beta carbon, and then the remainder of the R group. Beautiful. Let's go ahead then and note, as we already are aware, that this is L-isoleucine, as is true with all of our common 20 standard amino acids. But hey, look at that. We can now write the D stereoisomer or D enantiomer of isoleucine. So we know that's the second of our stereoisomers. So our D stereoisomer taking shape. Beautiful. But then, of course, we also know that there's stereochemistry around the beta carbon. So we can go ahead and write the other variation here, which is something called ALA isoleucine. So recognize then that this is allo-isoleucine. So I'm going to go ahead and try to fit the name of that down here. Allo-isoleucine. And then across our mirror plane, and there we have it, our D-allo-isoleucine. So all 4 of our possible stereoisomers of isoleucine all in one spot. Kind of overwhelming, but it's truly beautiful. Let's now return to our main notes and write down the 1 and 3 letter abbreviations for isoleucine. They're fairly straightforward, though the 3-letter abbreviation has a little nuance. It's ILE and then I. Again, as you're guessing, highly hydrophobic. So if valine likes a landlocked state, maybe isoleucine and leucine, like a state without even any lakes in it. So let's look at proline. Now let me tell you, if I have a, second favorite, I don't, let's say it this way, if I were an amino acid, I would want to be proline because quite simply it is so dang kinky. It has a beta carbon that then binds to a somewhat in a somewhat kinked way, because let me show you why. So beta gamma delta, and check this, this carbon binds back to the nitrogen. So this actually literally induces a ring type structure in the proline, and as you might imagine, this amino acid, wherever it might find itself within a protein, would introduce an abrupt direction change. That is, it would introduce a kink. So proline, PRO, 3-letter, P, 1-letter, restricts geometry and often introduces abrupt direction changes. As we turn our attention to the aromatic R groups, we'll begin with the simplest, phenylalanine. And in phenylalanine, the R group is quite simply a benzene ring. It will serve us well to recall our organic chemistry and the highly delocalized pi electron structure that we see within a benzene ring. Phenylalanine has a 3-letter abbreviation that you won't find particularly surprising. However, because we know that proline has already taken the P, F is going to be the 1-letter abbreviation for phenylalanine. One might readily assume that this is going to be very highly hydrophobic, and you would be absolutely correct. Lots of hydrocarbons. In fact, as we start thinking about things like benzene, we know that these are things that remind us of fuels or oils, and of course are very highly water-hating. The next one we'll look at is tyrosine, which looks very similar to phenylalanine, only it actually has a hydroxyl group in the para position of the ring. Hopefully that rings a bell, para position. And tyrosine has a 3-letter abbreviation that also makes sense. However, its 1-letter abbreviation is a Y, which is a little bit harder to remember. We do recall back to our earlier discussion about the fact that the more OH groups, the more polar OH groups you add to a chain of hydrocarbons, the more you increase its hydrophilicity, or its love of water. So recognize that tyrosine will be less hydrophobic, so the OH makes tyrosine a phenol. It is a phenolic, and it decreases the hydrophobicity. Less hydrophobic than phenylalanine. Let's look now at tryptophane, which I often joke is got such a big R group that you might literally trip over it. Tryptophane is a slightly more complex R group. This is attached to a 6-membered ring, all with highly delocalized pi electron structure. And that is, of course, the name of the game. And so recognize that that position there is a nitrogen. That's a little bit tricky to draw. So pi electron structure is the name of the game when it comes to these aromatic amino acids with strange 1-letter abbreviations. Tryptophane is W. It too is highly hydrophobic, as you might guess. And we recognize that this high pi structure, pi electron structure, the high delocalization, causes these amino acids to absorb light at wavelengths within the UV. So both tyrosine and tryptophane both absorb UV light at 280 nanometers. Thus, protein concentration can be determined by reading what we call A280s. Now, this is super applied. So say that you're working with a protein and you want to isolate that protein from a particular organism, a particular cell. Perhaps you lyse that cell, it releases its proteins, maybe you're able to partially purify the protein through dialysis, and then maybe you use some sort of chromatography to purify that protein further, and you want to know the concentration of the purified protein. You can look to read A280 readings, looking at a UV spectrophotometer that will measure light absorbance and will therefore tell you how concentrated your protein is in solution based upon the concentrations of tyrosine and tryptophane, because they absorb the UV light at 280 nanometers. So this is a fantastic applied way to see how phenylalanine, or to see how tyrosine and tryptophane are going to be pragmatically used in the lab to tell us how high our protein is in concentration. Before we leave the aromatic amino acids behind, I want to briefly draw your attention to the hydroxyl group again and tyrosine. And notice that although it is not ionized at typical physiological pHs, if you were to raise the pH to a higher, more alkaline pH, you might expect that there's a possibility that this hydrogen ion would actually be extracted from the OH, and that we would actually see that this could become reactive and maybe it participate in some sort of whether it be acid-base catalysis or some sort of nucleophilic attack, that the hydroxyl could become reactive if the hydrogen ion were extracted at high pHs. And in a cell, within an enzyme, we could see that locally that may be made possible by local electronic environment. And so that's something to bear in mind and keep in mind. So we're going to turn our attention now to looking at the sulfur-containing R groups. We have some truly exceptional amino acids. Methionine is fantastic because it contains a thioether. So I hope everybody has been reviewing the OChem review that I sent to you, and that you have reviewed what an ether looks like, recalling that it has this structure. If we have a thioether, then a sulfur replaces that oxygen. So a thioether would look like this. And methionine is famous for having a thioether. So it actually has an R group in which we see a CH2 bond S, bond CH2, bond CH3. Hey, another highly hydrophobic amino acid with a thioether. And a straightforward 1 and 3 letter abbreviation, MET and M. My pen likes to change color on me sometimes, so get used to it. It's black and blue. So recognizing then that methionine has a thioether. Now cysteine has a fantastic functional group as well. It has a CH2 bond SH. So we can recognize this sulfhydryl in the cysteine group, but also, just as we talked about looking at tyrosine, this SH group can become ionized. That is, it can lose its acidic proton, and it can actually act in a very reactive way. It can be involved in acid-base catalysis. It can most certainly lose that proton at more alkaline pHs primarily. So cysteine, again, 1-letter abbreviation and 3-letter abbreviation make quite a lot of sense. It is slightly or somewhat hydrophobic. It is highly reactive. and it can form weak hydrogen bonds, and it can act as an acid. It can become ionized. And we're going to see at the active site of enzymes, sometimes cysteine is going to get into the action. It's going to get a little bit jazzed about being able to act in a fairly reactive way at the active site of enzymes. So just as we saw a thioether in the R group of methionine, what we're recognizing that we see is a thiol. We see a thiol in the R group of cysteine, so a thioether and a thiol. Those are our sulfur-containing R groups. Now, we need to spend a little more time with cysteine because not only does it end up being reactive in maybe enzymatics, but it also is incredibly important in protein three-dimensional structure. So when we think about if two cysteine R groups in 3D space came close to one another, if we saw in the overall tertiary structure when a protein wraps around and folds, if two cysteine R groups come close to one another and the pH is slightly alkaline, then the sulfur can the two sulfurs in the neighboring cysteines can bind to one another, and it forms something that we call a cysteine, or more commonly called a disulfide bond. Disulfide bonds are incredibly important in overall 3D structure of proteins. So in order for two cysteine residues to form a disulfide bond, they have to become oxidized. So in order to become oxidized, it's assisted by a pH that's slightly more alkaline, so the likelihood goes up that the two sulfhydryls will lose their acidic proton and oxidation is more likely. We will see then that one cysteine residue in 3D proximity with another will form a bond between the two sulfurs, and that's what we can see taking place down in the picture below, where you have two neighboring cysteine residues then being oxidized and forming a cysteine, or more commonly called a disulfide bond. These disulfide bonds are going to really actively stabilize three-dimensional structure, and you can quite honestly see at a glance how this would potentially be the backbone to what might be pivotal to 3D structure in a protein, because if a protein folds, it goes through this hydrophobic collapse, and then there are neighboring cysteine residues. It might literally be like the crochet hook that holds together that region in 3D space. So these bonds play a big role in protein structure, and in fact we're going to look momentarily at how we sometimes exploit formation, breaking and reforming disulfide bonds to our advantage. And it's been a long time since getting a hair perm was in, but I certainly lived through a time when a perm was the thing to do. And so the way that that happens is that we actually break and reform disulfide bonds, therefore changing three-dimensional protein structure. So 3D structure, highly affected by disulfide bond formation.